Three, two, one, let's go. Bonus video. Okay. Alright, so we've covered everything that we needed to cover, but like I said, I wanted to sort of wrap things up with just, me splurging on some things that I like. Specifically, I frequently mentioned infinite dimensional vector spaces, and so today I want to kind of give you a sampling of how you actually go about studying and working with them. Okay, so let's recall some things. So a finite dimensional vector space is one who has a finite basis. Now there's two possibilities. So if your basis is the empty set, it's zero-dimensional, and this means that your vector space is trivial. It just consists of your identity element, and that's it. Not too interesting. Now, if there are a finite number of distinct linearly independent vectors that span V, that means that every element is uniquely represented as a linear combination of those particular vectors. Okay. So, basically, for finite dimensional vector spaces, we can study them from a purely algebraic standpoint. As we discussed, basically, all of this is just matrices in disguise, right? Even if we are dealing with, like, polynomials of a certain degree or other sorts of objects of a other sort of finite dimensional vector spaces, it's all just matrices one way or the other, and matrices are all about linear equations. Hence the name of the course, right? Linear algebra. So we basically spent a lot of our time talking about how do you actually handle finite dimensional vector spaces and how do matrices play a role in that. Okay. So then for the infinite dimensional case, there's still two possibilities. So the first one is if you're countable. So if there is a nice infinite list. So there's a first thing, a second thing, and a third thing. And note I started at 0 here. I counted incorrectly. But anyway, if you have a countable basis, that means you've got a list like this that's distinct, linearly independent, and spans V. So even though it's an infinite set, we can still represent everything as a unique finite sum, where basically you just need to go far out enough in the list in order to do it, and find the constants. So basically, anything with a countable basis is just the collection of all polynomials in disguise. So the v sub k's, you can just treat them as, instead of v sub k, think of it as v to the k. It's just the analog to x to the k. Okay. So, and again, polynomials can be studied pretty much purely from an algebraic standpoint. Some of the things, though, will require some calculus stuff. The intermediate value theorem certainly helps a lot with polynomials. But for the most part, you can study this purely algebraically. But what if you have an uncountable basis? All right. Now we're in the good stuff. So when it comes to infinite dimensional vector spaces, the countable ones are usually never considered because they're just polynomials in disguise. It's basically like scoffed at as just like, that's algebra. Get that out of here. So the classic example is the set of continuous functions. This is an uncountable basis. It's a little tricky to show that the basis has to be uncountable, but it's not impossible. Anyway, so the question then is, well, how do you deal with uncountable infinite dimensional vector spaces? Right, the set of continuous functions is very important, right, and within that the set of differentiable functions is very important, right, for solving differential equations, for example. So these are vector spaces that we encounter, and we'd like to be able to study them. So what tools do you need? Well, you're going to need things that go a little bit outside the scope of algebra. So specifically, the tools that we're going to need are actually something we've ran into in this class. So a norm on a vector space is a function that spits out positive real numbers, specifically non-negative real numbers, satisfying the following. The norm is 0 if and only if the thing you plugged into it was the identity element. If you scale something, then you can pull out the absolute value of the scaling, and if you plug in a summation, it's less than or equal to the sum of the norms. So if this is triggering something in your brain, that's because, well, we've already talked about this. This is basically the abstract version of what length is, right? So in R2, we define the norm, or the length, of a vector to be the sum of the squares of its components, which was based off of just, the Pythagorean theorem. Right, and in fact, we proved that actually satisfies these three conditions right here. Okay, so normed vector spaces are basically just an abstraction of Rn. But the good news is that they go a lot further than just Rn. They go to uncountable settings. So the usual norm on the set of continuous functions is defined to be the maximum the absolute value takes. Now remember, the extreme value theorem from calculus tells me that any continuous function will take its maximum value. And we pick the absolute value of f here so that the norm is always greater than or equal to 0, right? Because we want it to represent length, and so if it was spitting out negative numbers, that's not length. We don't want that. So there it is pictorially, if you want a good idea, a nice little parabola. So the norm then is the largest vertical distance away from the x-axis, is another way of thinking of it. If it goes negative, then right, you're just looking for the biggest distance from the axis. Now, I'm calling this the usual norm. It's also known as the uniform norm or the max norm. It's the norm you usually use for the continuous functions. There are other ones, but they tend to not be nice, let's just leave it at that. All right, so this gives us a way of measuring length of functions, right? So that's what we're going to say when we talk about a function's length. Okay. Now, what are we going to want to do with this? Well, we're going to basically want to use this to talk about convergence. And so here's the step now outside of the realm of algebra and heading into the world of calculus/analysis. So specifically, given a sequence in a norm vector space, it converges if given an epsilon, there is an n, so that, that needs to be a capital N. Oh no. That's, out of all the mistakes I've made, that is the single worst one. That is worth getting rid of my math license. Anyway, so there's a capital N so that x sub n minus x gets less than epsilon for all n greater than n. So for math 201, this is hopefully conjuring up nightmares of working with this. But anyway, yeah, so in norm vector space, since we have a notion of length, we actually can then talk about a notion of distance, which is the length of the difference. Right, the same way we did it in R2. Okay. So for some examples, in R2, if I were to give you the sequence that consisted of 1 over n and 1 plus 1 over n to the nth power, that converges, right? So the limit of 1 over n, it converges to 1. What the hell am I talking about? Man, that goes to 0. What do you... Yeesh. See, I got the trickier one right, the 1 plus 1 over n to the n. That's e. That does not converge to 1, that converges to e. Right, I know you feel like it's a 1 to infinity, right? But nope, not how it works. Right, and speaking of e, if you look at the functions, 1 plus x over n to the nth power, those are polynomials, by the way. The limit of those polynomials is e to the x. So in the set of continuous functions, that converges with respect to the uniform norm, the usual norm. As an example of something that doesn't converge, if you look at the power functions, x to the n, that's not going to converge to any continuous function, because if you look at the limit, well, x to the n, well, if x is between 1 and 0, exclusive of the 1, the limit will always be 0, right? So number less than 1 raised to a power is going to get really small. However, 1 to any power is always equal to 1, so that just sits at a 1. So that doesn't converge to anything. It was a very famous example of something not converging, actually. All right. So it turns out that convergence now, right, it's got a nice precise definition, but we can kind of just think of it as taking limits. Convergence now gives us a way of handling infinite dimensional vector spaces, because since we've got convergence, that means we can talk about series. Oh no. But yes. So, a Schauder basis for a norm vector space is a list, countable list, potentially finite, so that for any x, there are unique constants so that it's equal to the infinite series formed by that. Because we now have a notion of convergence, we can now talk about infinite summations. More precisely, the sequence of partial sums has to converge. Nice. So this now is kind of a better version of a basis for an infinite dimensional object, right? The usual notion of basis fails us in the uncountable case, right? It's uncountable, we don't want to deal with that. This is countable and allows for limits, right? And it allows for kind of the representation that we would expect. So this is kind of the right idea of an infinite version of a basis. All right, that sounds pretty good. So, pretty natural question then. Does the set of continuous functions actually have a Schauder basis? This is a name. Schauder is probably the right way of pronouncing it, but I'm going to say Schauder. But anyway, so does the set of continuous functions actually have such a thing? Now, your first reaction might be to use the polynomials 1, x squared, x cubed, but that's not going to work. Right, and why is it not going to work? Well, the things that you would form are power series. And yeah, those things are differentiable, and there are continuous functions that just don't have derivatives anywhere, so that's not going to work. So we're going to need something that is going to allow for non-differentiability. So we should immediately start thinking of things with corners. All right, so Schauder bases are named after Schauder, and specifically because he cooked up the following things for 0, and in fact he did it along with a guy named Faber. So we're about to talk about what's actually known as the Faber-Schauder basis. So specifically these delicious piecewise functions. So where the first one is the constant function 1, the next one is x, and the next couple of ones are these things. There's a typo there. Not like you care, though. They're just looking at this going like, what is this? What are you doing to me? I don't even need to watch this video. This is, I'm going to look at the analytics on this video, and it's going to be, it's going to just crash right now. Like, everyone's just noping out. Like, no, I don't need this. It's past the 10-minute mark. Everybody stopped watching anyway. Nobody's going to watch this video. I can say whatever I want. Fart. All right. Anyway, so what do these things look like? Well, the picture is a little bit easier. There are nice explicit formulas, but the picture is basically this. So you start off with the function 1. Then you start off with a function that is 0 at 0 and 1 at 1. You can pick anything that does that, but let's just go with the function x. The next thing you want to do is get a function at 0 at 0, 0 at 1, but 1 at 1/2. So this nice little yellow hat function right here, v2, works. Then you want a function that is 0 at 0, 0 at 1/2, 0 at 1, but 1 at 1/4. That's the green function right there. Right, notice identically 0 5 way forward. Then you want a function at 0 at 0, 0 at 1/2, 1 at 0 at 1/2, 1 at 3/4, 0 at 1/4 is what I meant, and 0 at 1. So basically what you're doing is you're taking what are known as the dyadic rationals, so the rational numbers in lowest forms whose denominators are powers of 2, and we're going to create functions that are 1 at one spot and 0 everywhere else. Okay, so then you keep going down the list. So then you would go to an eighth, so we create a function that is 1 at an eighth and 0 at all the other dyadic rationals. So far, you got to put them in a list, right, because there's some dyadics here that it's not equal to 0, and you basically just keep going. There's actually a nice way of creating these. So these triangle functions are known as hat functions, or also called chateau functions, to get real fancy. And basically it turns out that these end up being the right things to use, and here's why. Here's how you figure out the coefficients. So take any continuous function, don't care. At x equals 0, one of my functions for my list is non-zero, and all the other ones are 0. And at 0, it's 1. So we'll just choose alpha naught to be f of 0. At the next point, x equals 1, well, only 2 functions are non-zero. All the other ones were constructed to be 0 at these points. And note that if we were to add these up, we'd have 2, so let's divide out by 2. At x equals 1/2, all right, well, 3 of them are non-zero, but all the other ones are chosen to be 0. And the values that we have here for these are 1, 1 and a half. So we've got 5 halves, so that means we need to divide by 2/5, or multiply by 2/5. All right. And you keep going on the list. Now you go to 1/4. Well, you've got 3 points that are on 0, and all the other ones are 0. So add it all up. It's 11/4, and then make sure to scale it out so you're at 1. All right, and you continue this process. So then the infinite series that it forms will actually have to coincide with f of x for all values of x. Now, I note that it's not too hard, because note this procedure that I just described here is only going to tell you that for the dyadic rationals, the rational numbers whose lowest terms have a denominator who's a power of 2, right, the function will coincide with the series at those points. Now, here's where some hardcore calculus comes in. It turns out that the dyadic rationals are very well spread out, and so that means that our function f lines up with this pretty much everywhere, and because of continuity, that means it has to line up with it everywhere. So there's some work you need to do here to get this. But basically, once you show that it lines up on all the dyadic rationals, so note when you plug 0 into this formula on the right, everything except for the first term drops out, and then you just get alpha naught, which is f of 0, so 0 lines up. If you plug in 1, you get f of 1 on the left. On the right, everything but the first 2 terms drop out, so they add up to 2, and we made sure to divide by a half to get things to line up, so f of 1 equals f of 1. And there you go. So boom, that is a Schauder basis. In fact, it's the Faber Schauder basis, very famous example. It's not the only one that you can create. There are actually infinitely many Schauder bases. These are the ones that are the most nice. There's crazier ones that you can use. So note the set of points that I'm using to create it are the dyadic rationals. You can do the triadic rationals, which are the functions which are the rational numbers whose denominators are powers of 3. You can do the ones with the powers of 5, the quinadic rationals. You can do it with basically any prime, which, why would you do that? But you got that. If you want to go totally nuts, you can just use all the rational numbers, but those are a little harder to keep track of. Anyway, cool. Well, that's pretty exciting. So that gives us a way of creating a basis for a infinite dimensional vector space, a uncountable one, but a basis that's a lot more reasonable to handle, although now it involves infinite series and some calculus and analysis techniques, so it definitely goes outside of the realm of algebra. So let's wrap things up with a very famous problem. Does every infinite dimensional norm vector space actually have a Schauder basis? Okay. So, this was known as the basis problem. Now, it has its origins in the legendary Scottish cafe. So there was a cafe in Poland called the Scottish Cafe, because that was like its theme, where all the local mathematicians would hang out. And as math people do, they would just talk about mathematics because we're a bunch of insane people. And two of my favorite mathematicians, Stanislav Mazur and Stefan Banach, were hanging out. And Mazur had proven that you can always find a subspace that has a Schauder basis. So he was able to prove that in every normed infinite dimensional vector space, there is a subspace that possesses a Schauder basis. And Banach, after he looked at it, basically went like, okay, well, yeah, this should probably work then. The subspace then is the whole space itself, not a proper subspace. So I looked into the history here. Nobody knows for sure when Mazur actually did this. They know he did, because at the Scottish Cafe they had a book called the Scottish Book, where they would write problems, and in the book were these scribbled notes about, like, man, that original book, that would be something. It's as far as anyone knows, the original book has been destroyed, I think. Because if you look at the timeline, this is Poland, it's 1930s, things are about to not be good. Specifically, things did not end well for Stefan Banach, unfortunately. And yeah, Nazis can die. So yeah, Nazi punks, fuck off. There you go. Anyway, so yeah, so this was the prevailing idea. But like all wonderful prevailing ideas in the exciting world of analysis, and especially infinite dimensional vector spaces, oh, guess who shows up? Our good friend Per Inflow shows up, and he had a stellar year. 1973, he did it. He just like destroyed functional analysis. He came in and basically said, "Hey, all those problems you thought were true, yeah, no, they don't work." So yeah, a very famous paper with Per Inflow. He constructed the example showing that yeah, there's a subspace that works, but there couldn't be one for the whole space that worked. And as per Mazur's notes in the Scottish book, the prize was a goose. And here is Per Inflow winning the goose. He is very happy about it. Mazur is very disappointed that he had to fork over that goose. I love this picture. This is such a goofball picture. But anyway. Well, also, right, like I just said, Mazur was in Poland for World War II, so he saw, look at his face, he's seen some shit. But anyway, alright, cool. Well, there you go. So this just gives you kind of a sampling and a taste of what you do when you look at infinite dimensional vector spaces. And they're really neat, they're a lot of fun, and there's the history is so, like bittersweet, because basically all of it was happening in Poland in the 30s, and so many of them did not. Oh boy, yeah. Go check out the Scottish Cafe. They have a list of all the mathematicians, and they included, and next to their names are like, yeah, here's how they died. it's depressing. The math they did was so cool. It was so great. But yeah. Anyway, so let's just scratch the surface. If you're interested, check it out more. It's good stuff. All right. Hope you liked it. I'll see you next time.